You don't like the name? No, I don't.
What? Hey, that works.
Yeah.
What?
Nothing.
Yeah. They're very close to being done.
I knew it. How did I know?
I wanted to go over them today, but I gave some people who had issues with turning it in a bit of extra time. We'll go over the entire exam as a class. Every problem, so that you know which every single problem, not like I'm going to hold up your exam.
Oh.
We're going to go through the exam and I'm going to tell you what the right answer is. We're not going to do it today. No. So your last day to get the exam in, I mean, I have like all but 4 would be Tuesday morning. Okay. Well, whatever this time in class is for.
Yeah.
This morning for some people. I am so far pleased. Most people have gotten what I thought they would get and have not gotten what I did not think they would get. So that's good. Most people agreed with one another, which is really fun. It's one of the very first things I do, which is, I'll show you this. It's actually kind of fun. Here, hold on. So, because most of these are already together, I can do this. All right. I can show you this, I think. Okay. This is not how people have done. Okay, don't be worried. Okay, so you're freaking out. So here's your questions. And on the top is what people on average gave it being worth.
Oh.
So most people did not, you know, they really, really liked 1B and they didn't really like 1C. Okay. And over here on the right hand side, you see that everyone hated 5C. No one liked it. And the funny part about that is this is the standard deviation. This is like how random it was around the mean. So almost everyone picked that. So where these are small numbers, that's everyone agreed that this one sucked. Okay. So I do this first because this is really instructive to me to get feedback on what people liked and didn't like. And in general, you are thinking about what you did. And so I'm trying to understand and reward that. Okay, that's all you get to see. Don't take a picture. Okay. Anyone else still need to give me their exam? No, okay, different. Okay. Today we're going to talk about rings in. Oh, thank you. We're going to talk about rings in the Saturnian system, in the Uranian system, Jupiter system, and in Neptune system. And then we're going to talk about a couple moons, and that'll basically be it. We'll move on to like comets and asteroids and Pluto and stuff. So for Tuesday, you know, if you want to skip a day, don't skip that one, because that's the one that we'll go over the exam in detail. And I'll show you what I like to do with the final that I think you'll like. Okay, so said about everything I said. Okay. So you're familiar with this picture. I want this to go up. Okay, what? Okay, you've seen this picture before?
Yeah.
What is it? It's Saturn. Good. And you see Saturn's rings? Good. And is there anything else in this picture that you can see? I know it's far away. It's not a very good projector. What's that? The sun behind Saturn. Good.
That little bottom
corner, like the super right, yeah, that.
That? Yeah, that's like the diamond ring, no. That's just like the edge, so the sun is not perfectly behind, so it's just focusing there. There's actually a little dot here that I want to point out to you that's pretty cool.
I think they're all over it.
What?
They're all over it.
They're all over what?
The little dots, the white is like all over the blue.
Yeah, I'm pointing out this piece of dot right there.
Dust.
You think that's dust
Yeah.
on the projector?
Yeah.
But it's the same piece of dust that's over here on this projector?
You can't see it.
Oh, you can't see that one, so it doesn't count, right? No, I can't see it, it's not real. No, definitely. That's us. I mean, not me and you, like collectively. This is all of humanity, all of the humans that have ever lived and died are here in this dot. That is the Earth, as seen from the back of Saturn. Kind of fun, right? You would never think you could see Earth from Saturn, but just like Saturn can see Earth, we can see Saturn. Okay, so no more sleeping. That's enough. Okay. So Saturn's rings were the first ones to be found. Not surprisingly, you look at a telescope, it's pretty obvious. We talked about this briefly, they're separated by gaps, right? And we saw really kind of briefly that they have stuff that's in them, like moonlets. And it turns out that we talked a little bit about this thing called resonances. Do people remember what resonances are? Okay, when you're on a swing and you want to get going really high, right? Your brother or your cousin's pushing you, and they start pushing you at just random times because they're 6 and they haven't figured it out yet. It's really annoying. You can't get up. You want to get up really high. So when should they push you? Yeah, when you're at the very end, right? So they always push you at the end. That way you can get going really high. This is a version of resonant forcing. I'm pushing you at a specific time that keeps adding to your total energy, as opposed to hitting you randomly, which is sometimes making you slower and sometimes making you faster. This is only making you faster. Okay? So it turns out that orbits can have the same effect. We saw it when we saw Io. We saw it with Io, Europa, Ganymede, and Callisto. 3 of those are in resonance with one another. For every time that Ganymede goes around once, Europa goes around twice, and Io goes around 4 times. And we found out that when they're in that configuration, they pull on each other and they force each other. And that's what makes Io have these huge volcanoes, geologically active, even though it's tiny and small and made of ice. Okay? And so it turns out that that idea of resonance, being an orbital resonance with other things, is going to come back and show why these gaps exist, why rings exist, etc. For Saturn, they're very icy. Icy in our mind means like snow, and snow is dark or light? Light, it's very reflective. Okay? So that's why you can see Saturn reflective material. Okay? Ice. So another example. Anything fun that you see here? Like details about it? I don't see anything. We're not talking about the atmosphere. Atmosphere, boo. We're not going to talk about that again. Yeah.
I don't know if it's the lighting, but it looks like the rings closer to Saturn are lighter and the ones in the outer are darker.
Good. Yeah. So there's some like color differences here. And yeah, I would even say like there's not like a ring there. Right. So that could even be a difference. So there's definitely, it's like darker and then lighter and then lighter and then empty and then sort of dim, maybe. That? So there's structure in there. And we're going to see if we can attempt to explain any of the structure in the rings and why there's a hole in the ring. Why would there be a hole in the ring? Any guesses? Yes? Not quite. We'll get to that in a second. Let's zoom in here. Okay, that's a zoom in. This is from Cassini. Cassini was in orbit around Saturn for a really long time. Took lots of fun photos. In fact, most of the photos that we see of the Saturnian system up close from one spacecraft, a little bit from Voyager. Color doesn't look as good on this one. I don't know why. It's black and white. It's not a black and white photo right now. We're gonna talk about this section as we move in here, but even as we zoomed in, you can already see, we were talking about this having different color. Can anyone see this part here?
There's like 5.
Yeah, there's like really faint rings in there, right? 1, 2, 3, 4. Maybe if you have better eyes, you can find more. I don't have better eyes, but okay. Let's zoom in on this section. Let's see if we can see anything fun. Okay. Of course, we're really good at naming stuff. So this is ring A, B, C, and then F. Because as we got closer, we found more rings, but we'd already named them in the wrong order. So we should have named them from the interior going out, but we didn't. So they're A, B, and C. And there's of course D and E and F. But F was found after the other ones, so it goes on the outside. Astronomer is not great at naming stuff. And there's some fun stuff that we're going to point out here. This piece here, if we go back one, so that's this, right? We zoom in, we see that it's actually not totally empty. It's just faint stuff. And it turns out that we talked about that resonance, that idea of pushing. So stuff that's in here orbits orbits 2 times for every time that the moon minus goes around Saturn. Weird. So fact, this stuff here, every time that it goes around twice, minus goes around once. Exactly. And then this stuff out here has a different orbital period than this stuff in here. This stuff in here goes faster. This stuff out here goes slower. Farther you get away from the object, the slower you're going to orbit. Okay? This thing here is called the Encke gap, and this thing is called the Keeler gap. We're going to look at those. We're going to zoom way in here. Okay? Here's the Keeler gap. And go, moon. We kind of saw this picture before. We saw those like shadows passing by. Basically, what we're thinking about here, whatever this material is, it's being pulled and shepherded by these little moons. And you can literally see it. Okay, so I said, if we go back one picture, I said that this material is moving faster than this is, right? Okay, so let's imagine that we're standing here. You can think of it like you're on the freeway. And on the left-hand side, everyone's moving faster than you. On the right-hand side, everyone's moving slower than you. But you're sitting in your car. You really don't feel like you're moving. Let's say you're going at constant velocity. So it looks like everything's doing that, right? If you're pulling on everyone around you, then you're going to change what they look like after they pass you. So they pass you like this, and it goes wiggle, wiggle. And they pass you like this, and it goes wiggle behind you. And if you look, it's exactly what happens. This material hasn't met the Keeler gap yet. When it sees this guy, gets attracted to it, and goes, wee. It's fun. They're fat. They're flat. They're really, really wide, but they're very thin. So this is crazy to think about. Okay, to scale. I don't have anything that I can rip here. Yes, I can. Okay. So you think that this is the width of a piece of paper. If we do Saturn to scale, the rings are 1 kilometer across. It's big. Kilometer. They're so thin. What's 1,000 centimeters? 100 centimeters is a meter, and a meter is 3 feet or something. It's 30 feet wide. All of the material in Saturn's ring could basically fit from the floor up to the ceiling. It's giant. You can see it from Earth. It's bigger than Saturn. It's crazy. At least I think it's crazy. Maybe you hate it. Okay. Here's another one. So that moon in the Encke gap was Pan. I forget who's in Keeler gap. But actually, if you look very closely, all of these little, if we go backwards, they look like go all the way down. Here, smooth, right? No texture, no nothing. The closer we get, see these lines in here, different brightnesses. We keep getting closer, and even this place in here that looks smooth really has all these lines in it. Okay. And if you look very closely in here, you see all of this structure. It's not smooth, it's collimated into rows, are all orbiting the planet. Okay. You know the famous ring? There's also a ring you don't know about. Okay. It's called the Phoebe ring, and it's weird. So this is recent, 2009. This is Saturn. You have to imagine you're putting all of that material right here into this picture. Okay. So everything we know about Saturn sits in this little bubble, and there's this huge ring that you can't see with your eye. You can see with telescopes. There's a long integration pictures, and it's weird. It's tilted. Okay. They call it the ABCD ring plane because that's the name of the rings. The A ring, B ring, CD, right? Okay. So it's tilted 27 degrees. And it contains the moon Phoebe. Okay. It's probably formed from the moon Phoebe. Weird. So this moon over here on the left-hand side, this dark thing makes this giant amount of dust that is moving around Saturn. This one in here, Iapetus, I don't know if we'll get time to talk about him. Okay. Uranus rings were discovered next. Took a while. If you remember, Galileo found Saturn's rings. When was that approximately? Yeah, 1600s. This is almost 400 years later. You had to have really good telescopes. They use an airborne observatory. Such a cool excuse to go in a plane. Oh yeah, I need this plane to carry my telescope. Let's go. You fly really high, open the window. Pretty cool. There's a bunch of narrow rings. They don't have structure, or they have structure like Saturn's, but they're not shiny, which is kind of weird. So we talked about the fact that there's this major difference in the composition of Saturn and Jupiter compared to Uranus and Neptune. Uranus and Neptune are made up of material that has ammonia, that has methane, right? Whereas Jupiter and Saturn are mostly hydrogen and helium. And they're very icy. And I'm going to show you that that actually has a huge impact on the stuff that it looks like. Okay. They're not shiny, they're like rocky, which is weird. Here's Uranus's rings. Look how thin they are. So boring. Right? Look at this great naming convention. Epsilon, delta, gamma, eta, beta, alpha, 4, 5. Stupid. 4, 5, and 6. Okay, let's zoom in here. So we're gonna go look at this place. It's not really that cool. Super boring. Okay. If you take a long exposure, you can see it better. If you take a quick exposure, it looks like nothing. Long exposure, you finally get to see that there is material there. And here in the rings, there's all that structure similar to what we saw in Saturn. But you might be asking yourself, what the heck is that? You know, it looks like rainfall. These are stars in the background moving because Saturn and the spacecraft are moving together. So you take a long exposure, like you take a long exposure of the freeway, you see those little tracers. That's what's happening here. But this is moving with us. So the rings don't move. And only the background stars are moving. The only reason that I point this out is really obvious here how thin these rings are. Because you can see right through them. Stars you can see right through. Saturn's rings are so thick, I say that right after saying that they're not very thick, that they cast a shadow, right? So even though Saturn's rings are only 30 meters high, they cast a shadow. Sorry, 30 feet high. They cast a shadow. That's the important part to take away from. And you're going to see that rings are ephemeral creatures. So the fact that we can see rings right now is probably very coincidental. Jupiter's rings were discovered next, only 2 years later by Voyager 1. They're also detected from the ground. So their main ring, we kind of saw this already when we saw, how to say that properly, Adrastea and Metis. They orbit just inside and outside the main ring. They're actually closer than Io and the rest of the Galilean satellites. So you can see a faint halo above and below the main rings. So this is the picture. We look behind, again, it's Jupiter, and they're just very thin. Kind of cool. This is light coming through the atmosphere, bending through the atmosphere to our camera. This is what it looks like in the infrared. What does infrared tell us again? Yeah, it's how hot stuff is. And in fact, that's what we can see here. So we see heat that's coming from the planet, more at the poles. And then in that band structure that we've seen before, there are those little storms that are bringing heat up. You just saw that on Tuesday, right? So you can see that here. And you can see that there's definitely these rings. The particles in the rings are warm. Right? Even though they're in the cold of space, they're warm against the background of space. And so they're very easily visible here. And there's Metis, there's Adrastea. Fine? No. Okay. So this is sort of a normal picture of Jupiter's main ring. And again, when you do the long exposure, you can see that it's got this big halo that comes off of it. Really different than Saturn's ring, which is very thin, very confined. Different from Uranus's ring, very thin, very confined, right? And if we look even closer, okay, here's the left-hand side. This is a standard image, 10 times more sensitive, 20 times more sensitive, and 260 times more sensitive as you move out away from the planet. Okay, so here's Earth's orbit for scale. There's Metis, there's Adrastea, there's Amalthea, and Thebe. Main ring, weird rings. You don't need to memorize any of these. But this basic idea is you have all of this material in this ring. And it turns out every time that we see like these rings, they're associated with something that's orbiting Jupiter, for example. They're orbiting Saturn in, right, there's a correlation from its empty space and an orbital distance. Or you have a moonlet inside, which is messing with the ring particles. Okay. So these fainter rings match the vertical extent of these objects. Probably because they are providing the dust and the dirt. Okay, that makes these rings. So this material is getting blown off of the surface like a sandblaster. Okay, and that stuff then just begins to orbit Jupiter. What's doing the sandblasting?
What was your question?
What's doing the sandblasting? How is this material getting lifted off the surface of the moon? Storm. Storms? What kind of storms? Not exactly. These are too small to have any sort of erosion or atmosphere. They're very small. They're moonlets. So when we're in the dark of space, and we're orbiting Jupiter, what's the only thing that we care about? Yeah.
It was more like what happens with ions and how a lot of ions atmosphere get torn away by.
Yeah. So Io's atmosphere is torn away. It becomes the Io plume, definitely. But for these objects, there's no cryovolcanism. And I'm asking, how does stuff leave their surface?
Could it be gravitation?
They're small. I haven't necessarily said anything about them. What's protecting them? Anything protecting them? Do they have a thick atmosphere? No, they're small, so they don't have a thick atmosphere. They don't have cryovolcanism. So they're small and they have nothing to protect them. They are being sandblasted by particles from the sun. So light hits the surface, heats it up. Okay, you say, well, light's not really going to do anything. There's also little particles coming out of the sun, electrons, protons, helium atoms, and they're moving like 500 kilometers per second. Well, there's just tiny small things, who cares? But over a long time, you start to hit them, smash these particles, and as soon as they're liberated from the surface, they're like, bye. They just leave forever. Exactly like what happens with Io. As soon as a particle leaves the surface of the small moon, it has no reason to hang out with the moon anymore. It's only when it's encased in a mineral that it wants to hang out with the moon.
So would that be the hydrogen?
Yeah, so hydrogen coming off of the sun. Yeah. Called solar wind. It was one of the sources of loss of the atmosphere. We didn't talk about it in detail. For Mars currently, the primary source of loss. The fact that it's boiling off the atmosphere. Okay. Just like you can boil off an atmosphere, you can boil off the surface of a planet. Especially if they're icy planets. Okay, we'll come back to this idea. Neptune's rings, those were the cool ones. So, we saw Saturn was the first one, and then it was Uranus. Those rings were obvious, and then Jupiter. Now everyone's trying to publish really quickly. They're like, it's got to be rings on Neptune. And the first time that they saw a ring, it was actually a small moon. Cool, you discovered a moon, but you didn't discover what you thought you would discover. The first person who found Neptune was a Frenchman named Leverrier. They wanted to name, did you know that this is really funny? They wanted to name Neptune, not Neptune.
What were they naming it Leverrier?
Yeah. Can you imagine if we had Mercury, Mars, Venus, and Leverrier? That would be so annoying. Thankfully, cooler heads prevailed. Naming of all of these moons is really crazy. We'll talk about that in a few minutes. This is a lot of words. No one likes words. Okay, so here's Neptune's rings. In order to see them, it's like if you wanted to look at something close to the sun, do not look at the sun. Okay, so if I want to look, I just put my hand up and I stop the projector from blinding me so I can see the people below. That's what's happening here. So this is like the hand of the spacecraft. Okay, cover up the really bright thing. In this case, that's Neptune, and you can see the rings around it. Okay, these rings are funny, and I'll show you why they're funny in a few seconds. Can you see any reason why they might be funny to you?
One has more light on the right
From this side?
side. Right?
This side? Mm-hmm. So like that's the same ring. That's the same ring. That's the same ring, right? For different fonts?
It's like a different font.
Yeah. So I like that analogy. I haven't heard that before. Like a different font. What about this part here? Oh, weird thing one? What's that? It's broken up. It's not an optical illusion. It really is broken up. Okay. And they have names. There. Got a ring named after him. Stupid idiot. And it's an Adam's ring. I can't really see Lassell or Arago. I can see Leverrier and I can see Galilei. Let's zoom in here. There are arcs in the Adam's ring. This is from Voyager 2. These are real arcs. This is like material. It's all clumped up together and it's orbiting together like besties. Okay, they're all hanging out together. They're not equally distributed. And I don't know what's wrong with this presentation. They can't be very big. The rings are not solid. Okay, they're just little pieces of dust hanging out with each other. Now, it's probably mostly rocks. Even when we said Saturn was really icy and bright, it's like a rock with an icy cover on it. Does that make sense? So it's not like a snowball. It's like a snowball if you had a bully who really hated you. It's like a rock that they like froze and then threw at you. That's what you should think about when you think about rain particles. Okay. They're not larger than about 20 kilometers when you're thinking about these tiny moons like Metis and ASTR that we saw before. But they have really regular structure. And all of that structure seems to be tied to those shepherding satellites. We saw bending waves. I didn't actually show you any of these, sorry, but that exists. And the material in it is really small. Who has the most massive ring? Not in the room. Flex on me, okay?
You said the most now.
Yeah, which ring has the most total mass? Saturn. Is that obvious to folks? It's big. Big old ring. You can see it. Okay. It can only make about a 200, maybe 100 diameter moon. That's a small moon. And in fact, it probably recently was a very small moon. We'll talk about how that happened. Okay. Oh, we're right now. So essentially, rings are just debris. They're just leftovers. The problem is that if you think about it, so we talked about the fact that you have this moonlet and you sandblast the surface, and then this dust comes off of it, starts to orbit. But the light and the sun and all those particles are still impacting the dust. So it's getting ground down. They're colliding into each other. And if you don't replenish it, the rings disappear. So that means you have to continually replenish the rings. Which tells us that this is probably, I mean, you can think of the moonlets as leftovers, these little things left over from planet formation, but the rings are new. They have to be continuously refreshed. So for example, Saturn's ring is probably recent in geologic history, a destruction of a moon, maybe 100 kilometers. An icy moon, which would make sense because a lot of Saturn's moons that are close in are very icy. You use all that material, pull it apart, and turn it into a ring. A little home renovation project for Saturn. Okay. We know that we see that every planet's equator and main moon system lines up with the ring plane, which means they all probably form together, orbiting with one another. And every ring, as I'm about to show you, lies within this distance where the differential gravity, so how do I say this properly without being very confused? Okay. I'm Saturn. I'm pulling more on this than I'm pulling on this, because this is closer to me than this is, right? So if an object is big, I'm pulling more of this than I'm pulling that, this will want to come towards me. If I'm made out of just like tiny pieces of chalk that aren't very sticky and aren't holding themselves together, then these little pieces of chalk are just gonna be like, yeah, let's hang out. Okay, they're gonna be on their own orbit. And this other stuff is just gonna break up. You know. Okay. That's a ring, but you can't see it, sorry. Beautiful. Okay. Not a very good demonstration. I'll get a better demonstration. Okay, hold on. Let me show you. Okay, so this is a picture of if you take all of the rings and you smush them onto the same scale. If some of them are bigger, like larger, I'm just gonna physically shrink them. So the top, you have Jupiter, you have Saturn. Saturn's the one that we love. There's A, this is great naming convention. A, B, C, D, E, F, G. Really conveniently, look at this one. Enceladus, E. Oh, maybe they thought it all through. No, that's a coincidence. So what I'm going to show you here, take Neptune. Okay. Neptune has a few ones. It's got these arcs and it's got these shepherding moons, right? And in here, I said this word, orbital destruction distance for objects of density 1 gram per cubic centimeter. I remember that from somewhere. What's 1 gram per cubic centimeter?
What was your question? again?
What's
Sorry.
1 gram per cubic centimeter? Where are densities of 1 gram per cubic centimeter? I see many of them in this room. It's water. Water. Okay, so if you're mostly made of water, you will be destroyed inside of this little dotted line. This line, this line, this line, and this line. Okay? If you look at these moons, sort of briefly, they're mostly rocky. If they were not rocky, if they were icy only, they would be gone. This kind of makes sense because that's probably what Saturn's moon did. It was living out here, just living its best life. And then it was like, oh, I want to go say hi. And it got too close. And Saturn was like, I want to keep you. And then it just started taking pieces off. Every time you take a piece off the moon, now the moon's smaller, it's got less ability to hold on to itself. You just keep taking pieces of the moon's up. Cool ring though. Right? You see all of these ones here? Lots of Uranus moons. And they all shepherd these little ones. This one is stupid. Questions about the ring system? You won't have to memorize the ring system, I promise you. But the basic idea we're taking away from it is there's this interaction between the moons, lots of leftover moon pieces, and the rings. They feed the rings. Yeah.
Did all the planets have rings? Or
That's a good question that we will come back to when we think about planetary formation in like 2-3 weeks. There was probably very thick rings for something like Jupiter or something like Saturn when they started. And they would pull gas in order to get super big. Probably all started off as like rocky little things, but they got so big so fast, they started pulling in more gas, and the gas helped pull in more gas, runaway process. At Earth, it's unlikely that that happened because we don't have a very large gas envelope. So we don't think that Earth had a ring. If you're thinking about, well, why do we have a moon? That's a fun one. Does anyone know why we have a moon?
what's the question?
Why does Earth have a moon?
Is it because of the pollution when Earth
Yeah.
was green?
So there was like, we were like living our best life. We had a fully formed surface. We had volcanism and it was like cooling down. And then there was a cosmic drunk driver that smashed into us. And we're going to talk about this in a lot more detail in a couple weeks, but literally smashed into us, sort of a glancing blow, like hit the side of our car, so to speak, and smashed into us. Its interior went into our interior and it blew off our crust. The moon is mostly made of our crust. Isn't that weird?
So it absorbs our pollution?
No, in the past, a long time. It doesn't do anything for us now, except for give us tides, which are cute, I guess. I don't know. It's useless. Stupid moon. Okay, let's talk about more stupid moons. What's this on the right-hand side? A pumice stone for your foot? No. We won't actually get to talk about it. That's Hyperion. There are so many cool moons. We're only gonna, I don't even think we can get through all these. Mimas, you're gonna love Mimas, or some of you will. Titan, the coolest one. We've seen Enceladus before, but we're gonna tie back why we care about Enceladus to the rings. We saw it in the E-ring. Iapetus, we're just gonna also learn how to say fun names. Miranda, kind of a compared to the Russian. And Triton, as though Titan and Triton were not confusing enough. Okay. Quick question about here. Let's just test our, let's put on our, not forget everything that happened in the exam. Put on our geologic features. What do we see on this moon? Looks icy. Where do you see the ice?
Like where the white stuff is?
Yeah, like this region? Yeah, definitely icy. Cool. Anything else?
I would have said that would be erosion.
You would have
Like
said it
it-
was,
It looks like it's sliced, I guess.
yeah. So it looks kind of erosion-y. So like this, like it looks like it's like flowing. What were you saying?
not flowing, like slides, I guess,
Like slides, like a cliff.
yeah, like.
Yeah.
Way canyon from
Yeah. It's actually correct. So what's happening here is this is like a really icy, porous body. And so this thing here is an impact crater. But not all of these are impact craters. There's ice under the surface. And as it gets warm, it starts to leave. It says, I don't want to be in the rock anymore. And it blows off of the surface. And these are what are called sink pits. Just places where gas that's trapped underneath explodes. Okay. And then as that happens, there's these air pockets where the gas was, and it just slides or collapses. Oh, weird. You can also tell that it's not like how we normally think of objects on like the Earth or Mars, which are nice and round, despite what some people will tell you. And it has this weird shape. It means it's not very big. If it's not big, it's not circular. Okay, so when we see comets, they are going to look weird. They're going to look like potatoes. Okay, they're just like stuck together. Okay. Okay, come on. So, oh shoot, I was supposed to Saturn has the most of the. We're not going to talk about Jupiter's moons. We talked about Jupiter's moons. No one cares about Jupiter, right? You're sick and tired of Io. Don't want to hear about it. Okay, let's talk about fun things. So talk about Saturn's moons, 62 of them. We won't talk about 62 of them. Uranus, 27 of them. Neptune, 13. Look at all the moons. We only got one. Mars got 2. Not fair. Redistribute the moons. They're mostly called regular moons. Okay. Some of them are called irregular. Now, I know you're thinking, okay, we shouldn't label them, but we're going to. These ones are normal. These ones are weird. And I'll tell you why they're weird. Regular satellites. They're mostly all icy, and the really big ones we think melted all the way through. So they separated into rock at the middle, ice on the outside, crust ice at the top. Irregular ones probably didn't do that. They tend to be associated with rings, and they're very similar in composition to the ring. Okay. Here's an example. Here's Saturn's satellites and the rings put together. On the top, you see all of the rings and like moonlets. So like we talked about, like Pan, that's here deep in the ring. And these are the relative sizes. So up here, Titan's a big boy. Titan's real big. And there's Iapetus, Rhea, Dione, Tethys, and Enceladus, small. Small, okay? Epimetheus is just a fun one to say. Oh, and the radio station. And then Phoebe's out here being annoying. Phoebe makes the Phoebe ring. One. Okay. And if we look down here, here's Dione inside of the E-ring, Enceladus inside of the E-ring, Mimas inside of the E-ring, Rhea inside of the E-ring. And interestingly enough, this is the thickness, this part in gray. So it's pretty thick, and then it becomes not so thick around Enceladus, then it gets really thick as it goes out. Okay. Here's a fun one. What's that on the right hand side? It's Mimas, yeah. But it looks like the Death Star. Okay, yeah. That's all I wanted. I wanted somebody to be like, why are you showing Star Wars? Okay, so that's that, right? Okay, you've seen that. What? I should have flipped it so it looked the same. So interestingly enough, it's at the inner edge of the E-ring here. So that's Mimas. We're just going to talk about it because it's the one closest to the edge of the E-ring. And it's involved with that Cassini division that we talked about. So every time Mimas goes around once, that gap goes around twice. So stuff that's feeling attracted to it just gets pulled out of the way. It either gets pushed in or gets pulled out. Okay. And this one up here is called Herschel, the thing that gives it its picturesque Death Star shape. This is not a big move, and that's a big impact. Okay. So this thing, I mean, remember that these are like icy, rocky stuff. And so this probably came close to destroying the moon. And notice that it has this like rebounding thing in the middle. That's that central peak. We're not gonna spend a lot of time. Say bye to Marcus. It's just getting closer. This is the Cassini photos, as we flew by. Unfortunately, Cassini flew into Saturn, and so it's not in orbit anymore, RIP. And that means that these are the only pictures that we get for a really long time until we decide to go back. Okay. Let's see, what did I write here? Oh yeah, Mimas is heavily cratered. But what we don't quite understand, and you're welcome to decide to study if you want to become a grad student in planetary science, is why it's not being resurfaced. So Enceladus, we go back here. Enceladus is there. Right? What was Enceladus like again? What does the surface look like? What's that?
No.
Not as cratered. So Enceladus had these like tiger stripes on it, very white. South part of it had like fresh snow, it looked like. And yet Mimas is closer. This is a big, big question for folks who care about this question. Okay. I know not necessarily you, but for folks who care. Okay. This is the cool one. This is Titan. Titan is the second largest Saturn in. Titan is the second largest satellite. It's only slightly smaller than Ganymede. After the 4 Galilean satellites, that is Io, Europa, Callisto, and Ganymede, it was the first one discovered because it was big and it has a really reflective atmosphere. It has a dense atmosphere. It's got a denser atmosphere than we do. Okay, 1.6 times the pressure at the surface. Most of it's N2, nitrogen. Does not mean you could breathe here, right? What do we need? Not just nitrogen, oxygen. Yeah, cool. What could you do on Titan? You could fly on Titan. Okay, Titan's got a really thick atmosphere and it's small, not like the Earth. So every time that you did this, like right now you see you're just pushing air out of the way and I'm not moving anywhere. But you could literally flap your arms on Titan. Maybe you have to wear a little bit of a wingsuit, but you could like fly around on Titan. It'd be pretty cool. So that's why I like it the most. So here, the reason you can't see the surface, it's got a lot of hydrocarbons. It's got smog, and we're going to talk about that in a little bit. Anyone familiar with smog? Yeah, what's an example of smog? Just like every day? Okay, good, that's correct. So here's the left-hand side. This is a picture of Titan, as seen sort of illuminated a little bit from the back. And the cool thing about like haze layers, they're different from atmospheric layers in the way that we tend to think of them. Atmosphere seems like it's like very normal, right? There's no like sharp changes. But here you can see these like pieces in there. Right? See those pieces in there? Yeah, sometimes it's purple, has really cool color. It depends on what the haze is made out of. The word haze and smog we're going to use interchangeably here. So you say it's really hazy. I hear the word it's really smog. Okay. Hazes are just like the stuff that you burn out of your exhaust pipe. Okay. And then it collects in the atmosphere. Okay. So that's haze on Titan. And that's haze in LA. See those layers? It's got the same color too. Isn't that beautiful? So next time you're sitting in smoggy traffic, oh, it's just like Titan. You know? Okay, Titan's the best. I promise you. Okay, Titan is so cool. There's not very many impact craters. So even though we can't visibly see the surface, we can use radar to sort of map the surface. We can use infrared to look for heat signatures. And there's evidence of cryovolcanism. Okay, so the interior of the planet is molten ice, which you interpret as molten ice? Water. Okay, good. So water sits at pressure underneath the surface, trying to get out. It doesn't want to be under pressure. And so it finds a little crack in the surface, and says, I'm here. But where on Enceladus, it would just shoot up into space and disappear forever. It's a thick atmosphere. So it hangs out. And it becomes liquid. Okay. So here's one of Titan's cryovolcanoes. It's a zoomed in picture. It's not a very good picture, I'm not gonna lie. Here is the only body in the solar system have liquids permanently on the surface. It's here. This is Ontario Locus. That's the South Pole. These are clouds. There is a whole hydrological cycle here. I should be careful though. It's not really hydrology. I said water, but it's not really water. It's nitrogen ices. So you can't drink them, you can't play in them. You can, they just won't be as refreshing. So you see several lakes near the poles, and they change their depth and time. There are rivers that flow into them, and they're massive. Okay, I'll show you that in a few seconds. So here you see deltas. See this stuff? It looks like what is it? So you see how it like goes out in this fan shape? It's a place where like you're depositing sediments. So there's active geology on Titan, and there's this giant lake. You say, okay, well, it doesn't look that big. It's not a very good picture. This is 90 kilometers. So for context, this is Lake Ontario on the right, but on the same scale. Where's Lake Ontario? What country?
Canada.
US and Canada, yeah, perfect. In between. The Great Lakes, folks familiar with the Great Lakes?
Michigan.
Yeah, near Michigan. Really not know where the Great Lakes are? Shit. One person, okay. It's big. They're called Great Lakes because they're big. This is supposed to be impressive, but if you don't know what a Great Lake is, then it's not very impressive. Okay.
They have waves though, too, right?
Yeah, they have waves. That's absolutely true. So they have waves, they are like massive things, and we do think, in fact, that there indeed are waves here. Right? Because you can, if you look at the surface, you can see that they're large enough that they would have tides. Just like the way that the oceans have tides. You can only have tides on really large bodies of water. Because otherwise they're just like a pool. Your pool doesn't go up and down twice a day, right? Okay. Here's another example. This is on the same, so on the right hand side, that's the Earth, don't get confused. On the left hand side, that is I forgot what the name of it is. I didn't put it up there. North Polar Great Lake? I don't know if that's true. But you can see it in this photo. So when we were first introduced to Titan, I showed you a picture of it being illuminated sort of from the back and like light glistening off of the lake surface. That's what you're seeing here. Titan, just the coolest. We dropped a lander called Huygens, which safely penetrated the atmosphere. It landed. This is like the opposite of the Venus problem we had. So what happened to our landers on Venus? They just melted. Yeah, they were just like, no. These ones do the same thing, but backwards. These freeze. They're just so cold that we can't keep them awake for long enough. So we're gonna try again. We're gonna send something called Dragonfly. Super cool. Also cool name. Wait. Oh god. Okay. Anyway. I don't even know why I try. Okay. Dragonfly is great. So what is it gonna look for? So I told you we can fly, right? So they were like, well, let's send something that can fly. So they're gonna send a rotocopter to Titan. They're gonna land it, and they're gonna fly around from lake to lake. And they're gonna be like, what's in you? And they're just gonna pick stuff up and look at it. And so what you're seeing here is they're going to try to assess microbial habitability. Because we have stuff that's on the surface, like a lake. There are sources of heat, and there's complex photochemistry. We think that there could potentially be life there. Okay, let's see what else we got. We saw a moon. This one sucks, right? Boring compared to Titan. But here's Enceladus's tiger stripes again, oriented here. They're named after the rivers in the Mesopotamian region. And here you have your craters, blah, 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 fully resurfaced, not resurfaced. Only have heating in the southern hemisphere. Enceladus' surface is young, we already mentioned that. But you also see that there's these cracks in them, right? This fracturing, that's due to the fact that it's being resurfaced and the surface itself is motile, right? So it's been identified that these particles are the one that are forming the entire E ring, right? You can see that happening because we flew by and we watched it happen. So this is the southern hemisphere where the tiger stripes are. This is particles coming out, and this is from afar, realizing, oh, this is why it's so small near Enceladus, and it gets bigger elsewhere. Particles start here, and I go. This one's fun. We can't talk about it for very long, but it's one of my favorite moons. Is Iapetus, the walnut. It helps us to date the Saturn system as a whole, because it must have formed. We can figure out, like, from the heating that the entire Saturnian system was formed in like 200 million years, like a blink of an eye in geologic time frames. Plus, it's cool. It looks like a walnut. What? Okay, old moon, weird ring. Okay, well, one more. This is a family portrait of the Uranian system. Uranus is really weird because it orbits like this. Okay, so this is the rotational axis. It's pointing right at the sun almost. The whole system's turning over like that. So all of these moons are pointing around, they're turning like that. Okay. It's got weird names like Miranda, Ariel, Umbriel, Titania, and Oberon. They're on the common scale here. We're not going to spend a lot of time there. We're only going to talk about one of them. Triton. This is Neptune's only major moon. It was in that picture, the JWST picture. It's 200 times more massive than the rest. It's twice the mass of Pluto. Okay, so you're already going to start to see this conversation. Someone asked me about this. Well, what's a planet? Uh-oh. This thing is bigger than Pluto. Is it a planet? You think it's a planet? Got one vote for a planet. Let's see how many people decide that. It's a little bit smaller than Europa, but it must have been captured. And the amazing thing is it's going to be destroyed. It's on a really weird orbit. It's headed towards Neptune. And we can talk about this when we talk about our moon and Venus's moon. Venus, one of my favorite unprovable hypotheses about Venus is that Venus was hit twice, 2 moon forming events, and the second moon forming event caused both of its moons to collapse into it, and that's why it spins so slowly and it's so awful to live on. But it's impossible to prove because the entire surface melts every 600 million years, so we can't even get to anything old. Crazy. Triton has a tenuous atmosphere, in case you didn't immediately see that. So even though this looks super fuzzy, it's not just fuzzy, like there's stuff in the way. It's not as big as Titan, it's not cool. But it has cryovolcanics, which is sick. Very young surface, not nearly as heavily cratered. And it has like ice plate tectonics. It's really sick. You can imagine like ice plates going into it. Okay. Here's an example of that. What does that look like to you? What's that? Sure. And what item in the grocery store does it look like? The right answer is a cantaloupe. Oh, look at that material there. Okay, cantaloupe. You don't see that? Am I the only one who see that? Okay. All right. Oh, yeah, this could be like sherbet ice cream. Yeah, so you can see a lot of things in here. So the structures that you saw in here are these fractures. There's pitting, and then what is this black stuff here? It's been hit in a lot of places, but I actually don't see any impact craters in this picture.
It's burnt.
It's burnt?
Yes.
Where What do you mean by that?
It was and that's like the residue.
Okay, okay. What? Yeah, there might be some sinkholes in this picture. What did I say 2 seconds ago? I was talking about, before I was talking about that weird change about cantaloupes. It has a young surface. Why does it have a young surface? So when you say it's burnt, it's not that far off, like an explosion of material, but it's not like hot in the sense of like we think it's hot. It's like hot for that system, right? So these are in fact streaks of material coming out from the interior and laying down new material on top of the existing product. And it's not really a good picture. I'm not. But you can see it very clearly here. So in the middle, not clearly. You can see it kind of clearly here. So if you look in the middle, you see this little dot, and then you see these plumes that blow out. So this would be like you have some cryovolcanism, and as the material gets ejected, there's a preferred direction, and then it just lands back down. Okay.
What is cryovolcanism mean?
Cryovolcanism is the process of when you have some, let's say, whether it's water or it's some sort of ammoniated gas, you put it under pressure, and it's underneath the crust. It doesn't want to be under the crust, so it finds a little hole, little volcano, and it jumps out. Okay? And usually on small moons like this, some of it will have orbital escape velocity, and it'll just be able to fly away, and some of it will land and make these little plumes. Okay.
Like the hot spots, like on spring.
You mean like a pool
Yeah.
that you get into? You wouldn't want to get into them. Think of them as like geysers. Does that make sense? Like Old Faithful, but cold. Cold faithful. Okay. Okay, so that's all the moons I want to show you. I know that was a lot of information. There wasn't a lot of like questions. We're gonna go back to comments and all of those materials. So we're gonna use a lot of this, but we're gonna talk about it in the context of sublimation. And today we have an observatory open house at 7:30. On Saturday, we will have another one, I believe at 8. That's for the homecoming event. You're welcome to come to either. My assumption is that the homecoming event will be crazy. Like 200, 300 people that normally go to that thing. And then on Tuesday, we'll go over the exam in detail. I would highly recommend that if you have a friend not here, you tell them that that is the day to not miss, or to consider reading the, what is it called, the recording. Questions before you finish for the day? Yeah.
So, for example, if will the moons of some of the planets turn into rings?
Yes.
If it is possible.
This one. This one is headed on a collision course. And in like 3.5 billion years, some of you will be around for that, some of you won't be. This will be a beautiful ring of Neptune. Put that. Your calendar, yeah. Circle that one, 3.5 billion years. Bye-bye. Okay, thanks everyone. Any other questions? Oh, hell yeah. Am I gonna miss it? I saw solar eclipse. I want to watch this thing disappear. Sick. Tonight. Let's have one on Saturday. Kind of going like, yeah, in one direction. Yeah. I don't know if that's what's going on here. I would assume that there is some sort of like wind blowing it by.
Yeah.
Very thin atmosphere, but it is an atmosphere.
Okay, yeah, that was wondering.
Where's the train, where do you get to, sorry? Is there a parking lot there, or?
Yes, there's parking lot there. So, have you seen the observatory from campus?
I mean, I think I'll see you over there.
Yeah, so if you head out, if you think about the end parking lot right there. Yeah, let me just show you on here. Oh, wait, shit, stop the recording. I don't think anyone listens to these anyway. Where is it? Did I? No, I didn't.